Today we are going to discuss about design of IIR filter and methods of IIR filters. And here the IIR filters, there are two important features of IIR filter. The first one is physical realizable IIR filters does not have linear phase, and the second important features are the IIR filter characteristics for the only man-to response. Next, there are four methods used for converting the analog filter into a digital filter. The first one is approximation of derivatives. Second, impulse invariant transformation. Third, the bilinear transformation. Fourth, the matched Z transform technique. So let's see one by one in detail. So what's a design of IIR filter using impulse invariance technique? So in impulse invariance method, the impulse response, how will you find this impulse response of the digital filter? So the impulse response H of n of a digital filter is the sampled version of the impulse response of analog filter. So that can be written as H of n is equal to HEA of t. Now taking the sampling at time t is equal to nt. So we get this impulse response of digital filter. So H of n is equal to HEA of t, and replace t is equal to nt. We get this HEA of nt. So here the digital filter with the frequency response characteristics is corresponding the analog filter if the sampling period t is selected small to minimize the effects of aliasing. Now we derive the impulse invariance technique of the impulse response. Let HA of S is the system function of the analog filter with the distinct poles. It can be expressed by a partial fraction form. HA of S is equal to summation k is equal to 1 to n Ck by S minus Pk, where here Pk are the poles of the analog filter and Ck are the coefficients in the partial fraction expansion. Now taking the inverse Laplace transform of HA of S, we get this HA of t. So HA of t is equal to C1 e power P1 of t plus C2 e power P2 of t, etc. up to Cn e power Pn of t. Now the HA of t is taking this all the terms are summed. So we get HA of t is equal to summation k is equal to 1 to n Ck e power Pkt, where t is greater than or equal to 0. And from the equation 2, now taking the sampled and at t is equal to nt. So H of n impulse response of digital filter, H of n is equal to HA of nt. So this equation 2 can be written as HA of n is equal to summation k is equal to 1 to n Ck e power Pk nt. Now we derive this H of z. So H of z is equal to summation n is equal to 0 to infinity H of n z power minus n. Now substitute here H of n expression. So H of z is equal to summation n is equal to 0 to infinity into summation k is equal to 1 to n Ck e power Pk nt into z power minus 1, and the rearranging the summation term. So summation k is equal to 1 to n Ck and summation n is equal to 0 to infinity e power Pk t z power minus 1 whole power n. So the second summation is termed as a 1 divided by 1 minus a formula, summation infinite series formula. Now substitute here summation infinite series formula. So the H of z equation can be written as is H of z is equal to summation k is equal to 1 to n Ck divided by 1 minus e power Pkt z power minus 1. So if HA of is equal to summation k equal to 1 Ck divided by S minus Pk is nothing but analog filter. So this system function of the analog filter is converted into system function of the digital filter by using the Z transform. So H of Z is equal to summation k is equal to 1 to n Ck divided by 1 minus e power Pkt Z power minus 1. For example, here sampling rate is high means the digital filter gain is also high. So this above equation we can written as H of z is equal to summation k is equal to 1 to n t Ck divided by 1 minus e power Pkt z power minus 1, where t is a sampling period. So now due to the presence of aliasing, what's aliasing? Aliasing nothing but the overlapping between this higher component and the lower components, now called as a aliasing. So now due to the impulse invariance method, due to the presence of aliasing, the impulse invariant method is used only for low pass filter and band pass filter, and it is not used for the it is not used for implementing digital filter for the high pass filter. So now we design the digital filter using impulse invariant method for the following steps. The first step, for the given specification, first to find the transfer function, system function of an analog filter, and the second step, select the sampling rate of the digital filter, sampling rate. Now select the sampling rate. Second, third step, express the analog filter transfer function as the sum of single pole filters. That's formula is a HA of S is equal to summation k is equal to 1 to n Ck divided by S minus Pk. And from this transfer function of the analog filter is converted into digital filter using the Z transform. So that formula is H of Z is equal to summation k is equal to 1 to n Ck divided by 1 minus e power Pkt divided by Z power minus 1. For high sampling rate means we can use this this expression. H of Z is equal to summation k is equal to 1 to n t Ck divided by 1 minus e power Pk t Z power minus 1. So now we discuss the what's the relation between analog poles and digital pole. So if sigma is a real part, so if sigma less than 0, then analog poles is lying on the left half of the S plane is mapped into the digital pole inside the unit circle. If sigma is greater than 0 means all the poles in the right half of the S plane is mapped into the digital pole outside the unit circle. If sigma is equal to 0, the analog pole lying on the imaginary axis is corresponding mapped into the digital pole lying on the unit circle in the Z plane. So in the imaginary axis is mapped into the unit circle, it is not 1-to-1 mapping, it is rather than into the many-to-one mapping. So it is a many-to-one mapping method. Impulse invariant method is a many-to-one mapping. So many point in the S plane are mapped into the single point in the Z plane. This is the main disadvantage of the impulse invariant techniques. The impulse invariant method is not 1-to-1 mapping, it is a many-to-one mapping. So this it's a infinite number of S plane points that map into the same location in the Z plane. So that's a produces the aliasing effect. So this is a main disadvantage of the impulse invariant method. So impulse invariant technique. So the what's a impulse invariant method is the many point in S planes are mapped into the single point in Z plane. So that's why that's to producing the aliasing effect. So this is a main disadvantage of the impulse invariant mapping. So due to this spectrum aliasing, so the impulse invariant method is not used for the designing the high pass filter. So now we solve the problem for the impulse invariant method. For the analog filter transformation, H of Z is equal to S into S plus 1 into S plus 2. And now determine the H of Z using impulse invariance method and assume t is equal to 1 second. So the given specification is a analog transfer function. Analog transfer function H of Z is equal to 2 divided by S plus 1 into S plus 2. And the sampling period t is equal to 1 second. First we apply the partial fraction expansion. H of Z equal to a divided by S plus 1 plus p divided by S plus 2. Now using this partial fraction expansion formula, now solving this for equation. Now so 2 is equal to a into s, now cross multiply. So 2 into a into s plus 2 and plus p into s plus 1. Now first substitute s is equal to minus 2 in the equation. So t is equal to minus b. The b values is a minus 2. Now substitute s is equal to minus 1 in the equation. So we get the value, we get a value is a 2. Now the a value and b value substituting here, H of s expression. So H of s is H of s is equal to 2 divided by s plus 1 minus 2 divided by s plus 2. Okay, now using the impulse invariant method, now the analog transfer function is converted into digital filter using this Z transform formula. So that's a H of Z is equal to summation k is equal to 1 to n Ck divided by 1 minus e power Pkt Z power minus 1. Here there are two poles, one is a P1 pole, P1 is a minus 1 and second pole P2 is a minus 2. Now here the summation terms is summation H of Z equal to summation k is equal to 1 to 2 Ck divided by 1 minus e power Pkt Z power minus 1. Here t sampling period is a 1. Now here expanding the summation term, So h of z is equal to 2 divided by, so the c1 divided by 1 minus e power p1 t z power minus 1 plus c2 divided by 1 minus e power p2 t z power minus 1. Here see what's the c1 value? C1 value is 2 and c2 values are minus 2. So h of z is equal to 2 divided by 1 minus e power minus t z power minus 1 and minus 2 divided by 1 minus e power minus 2 t z power minus 1. Now substitute here sampling period is a 1 second in the h of z expression. So h of z is equal to 2 divided by 1 minus e power minus 1 z power minus 1 minus 2 divided by 1 minus e power minus 2 z power minus 1. Here e power minus 1 values is a 0.3678 and e power minus 2 values is a 0.1353. Now cross multiply this expression and cross multiply and simplify. So finally we get h of z is equal to 0.465 z power minus 1 divided by 1 minus 0.503 z power minus 1 plus 0.04976 z power minus 2 z power minus 2. Thank you.